Okay, this is a video segment for modeling axisymmetric contact in the 3D Experience finite element program. Uh, it belongs to the playlist, which is for the people who want to make a transition from the ABAQUS CAE to the 3D Experience, or who are entirely new to 3D Experience. Mind you that the FEA solver in the 3D Experience is actually the ABAQUS program. So the process behind making these videos is that I take certain tutorials which are available on YouTube, and they have been done by uh, people using 3D using the ABAQUS program in a step-by-step way. In other words, it shows you all the processes that you have to go through, all the clicks that you need to do in the ABAQUS CAE in order to get to the end. So I will replicate those in the 3D Experience interface. Mind you that although the software is the same, the solver is the same, the interface is different, the icon is different, and it's an entirely new ball game basically. So I'm indebted to David Martin of the SAS system, who gave me valuable information and the know-how on how to do axisymmetric modeling in 3D Experience. The problem that I'm going to be doing is actually the work of this gentleman. Uh, it's a very good tutorial which shows you how to do this problem in the ABAQUS CAE, except that some of the things that he's doing is not going to be in this particular video. Okay, the problem is the same, but I will prepare two other videos which are doing the same problem using the axis symmetry, but in a different way. Okay, so basically we have an indenter which is pressing very rigid, which is pressing against this workpiece. Okay, and uh, we are. I will be solving this thing uh, by making the indenter a rigid entity, and of course the deformable one is down here, which is the workpiece. Okay, uh, in the work of this gentleman, he's doing this as a axisymmetric problem, but the indenter is made as uh, basically beam elements. Okay, and that's not the approach in this video. Okay, so I will be using the same material properties that this gentleman is using. So it's given here, and the dimensions of the workpiece and the indenter are there. Uh, Basically, this graph, which is plastic strain against the true stress, is given by this information. Young's modulus Poisson ratio is there, and we'll get to these things later on. So I will bring them up. Actually, I'll put it momentarily on the screen, but we'll get to these later on. Okay. So let me go ahead and uh, here is the 3D experience. So I've started already an assembly file because this is going to be interaction between two parts, the indenter and the workpiece. So I'm going to call this thing properties. I'm going to call this assembly. I'll call it uh, axisymmetric. Uh, I will call it continuum. And the reason I do this is that I'm modeling both the workpiece and the indenter as continuum elements. Okay, so good. Let's insert our first part in it. Uh, insert 3D part. This is going to be my workpiece. So I'm going to double click on it. Double click on 3D shape. Let's get rid of this. And on the YZ plane, I will sketch that rectangle that is going to be the workpiece after you revolve it using the axisymmetric concept. So right there. Let's give it some dimensions. This was 25. This is 25 millimeter. and this height is 10 millimeters. Exit. And we have to create a three-dimensional object out of this, although eventually it's going to be solved as an axisymmetric problem internally, but you really have to create the three-dimensional object in it. So there's going to be a shaft of that sketch about the z-axis for 360 degrees. So this is going to be the workpiece, okay? I mean, I don't know, I can call this thing workpiece, or I can leave it the way it is, or just leave it the way it is. The first part is the workpiece, okay? Now, let's define two things, because for axisymmetric geometries, I need a point and the axis of symmetry, which incidentally does not have to be the global z-axis. So what I'm going to do is I'm going to create, and it's important to do this thing in this point, which is defining the origin of the axisymmetric basically geometry. It has to be in a geometric set. So I'm going to create a geometric set. I'll just leave it default name, and in it I create a point with coordinates 0, 0, 0, which is going to be eventually used as my axis of or the origin of the axisymmetric geometry. Okay, and then I create instead of creating a line there in that geometric set, I'm going to click on the axis system. It automatically will create an axis system at the origin for me, and that's really what I want. And I'm going to use its z-axis as the axis of symmetry. Okay, so I'll check this, I uncheck this current. There we are. Okay, let's apply a material. So we go to tools, material. Well, actually create a material instead of material browser. I already created the material, but I will create another one. So let me see this. Create material, and I'll call it. I think it is brass. Actually, that property is for roughly brass. Or here, I'll call it brown. Actually, you know what? I'm going to call it workpiece. How about that? Workpiece. Okay, workpiece, and say okay. Right now it's a template, there's nothing in it. So it's going to be created in just a second. We're right here, right click, apply. I'm going to close this, and I'm going to apply it to this indenter right there, that 3D part. It's called physical product, but that's where it is. Now I'm going to put in the values. So let's go here, double click on material branch here, and we put our numbers. Okay, let's move this thing out of the way. It's a structural, it's a ABAQUS multi-physics, mechanical, elasticity, elastic. I believe the Young's modulus was 100,000 MPa, and the Poisson ratio was 0.34. Okay, let's double check on that. Young's modulus was 100,000, Poisson ratio 0.34, and then we have to input the plasticity stuff. So we go to plastic, metal plasticity, plastic, and I will put that the yield strength is let's see, it was 110 at 0 plastic strain. That means initial yield strength. And the next point that I'm using shows hardening here, 300 at 0.8 strain. So 300 at 0.8 plastic strain. We can, by the way, plot this thing. You put the cursor there, right-click plot. It shows you that graph, which is basically what I had on the slide. Close that. Say OK. Let's quickly save this. And now we're going to insert our indenter. So we go to the top level, the assembly, right click, insert, 3D part. This is going to be the indenter. So I'm going to double click on it. And on the same YZ plane that I do that triangle and shaft, basically revolved it or shafted it, I'm going to sketch that circle, half a circle, semicircle. So on the essential, we go there. I'm going to draw an arc. Let's put the center here. Oh, oh. Try it again. Center here. We start on the top. And there's my arc. Okay. The radius of this was 5 millimeter. Okay, I want this thing to come down and sit on that workpiece. So the different ways of doing it, for example, you can do this point. You can do dimension between this point and this top line. And either make it 0 or right click coincident, it'll bring it down and put it there. Okay, I also need a line here. We also need a line there because we're going to shaft this thing eventually and make a sphere out of it. There is my, let me see, I can't see this. To this point, the line between this point and that point. Okay, good. I don't think these are actually coincident yet. So this point, the different ways again to make it coincident. This point and that point. Let me see. Let's look at the view from the front actually. There. It have to close this thing. View from the front. So this point control that point. Yeah, not. Well, actually, we can make that dimension 0. How about that? That was a bad idea. Okay, good. Wasted some time here. Okay, good. Now we're going to exit and once again shaft this. Shaft it about z-axis 360 degrees. Very good. Now, because I'm going to be using this thing as with meshing it with continuum elements, I believe that you're going to have neat material properties. Eventually, this is going to be declared as rigid, but I have a feeling that if you don't declare material properties on it, it's going to complain, and then we have to go fix it and things like that. So while we are at it, let's go ahead and do that. So we apply some dummy material on this thing, but it needs to have a material property, and I'm pretty sure about that. So you go to once again tools, create a material. I'll say indenter. Let's say okay. Right click apply. I'm going to close that. I'm going to put it on that, put it on that part, and now we're going to put some numbers in there. Let's say that this is made out of steel, so something a lot stiffer than the other one. That's why it's acting as basically rigid. ABAQUS multiphysics, mechanical, elasticity, elastic, and I'm going to put let's say 200 gigapascal, roughly 2,000 times stiffer than that thing that I put up as the workpiece. Okay, so 0.3 doesn't matter, but I'm pretty sure you need to have a material on there. Okay, good. So this is it. Now, ordinarily, in most of my video segments, except for the ones on Axisymmetric, at this point, I used to go to, see for a second. structural model creation. The problem is that if you go there for meshing purposes, you're not going to see the axisymmetric option. So what you need to do is to go to this thing called model assembly design. But before doing that, so that you don't get confused, let's go to all the way to the top level, all the way to the top level, okay? Because right now I'm sitting at this part. We're going to go all the way to the top level, and now go to that thing that I mentioned, model assembly design, instead of structural model creation, because here you have axisymmetric option, here you don't. You click on it, and when you get this, you go to automated FM. So that's what this slide was that I stopped. Okay, I stopped right there. When you click on this option is going to pop up. Automated, see, automated FEM right there. So let's do that. Automated FEM, and we're going to use the axisymmetric option, and it's going to ask us some questions. First of all, it says, what is the plane where you actually drew your sketches in? And in both cases, in the YZ plane. It can be an arbitrary plane, by the way. I use YZ because it was convenient. It says, what is the origin of that axisymmetric geometry? So it's this point that I created and put it in geometrical set. Okay. What is the axis? The axis of could have drawn a line and put it in that geometrical set, or I can use this Z coordinate system that I created. See that? See that? The Z axis, or a line if I had there. Now it says, okay, do you want to, how do you want to mesh? I want everything that's visible. Both of these are visible, and I'm going to mesh it. Okay. Otherwise, you go and select whatever you want. And finally, it says what is the size. Okay, I'm going to use first of all bilinear, means bilinear element with the size of 0.3. And the reason I use 0.3 because it's compatible with that site that I saw, that link that I showed you on uh, the ABAQUS CAE version of this particular tutorial. He's using 0.3, I'm using 0.3. We say okay, and just give it 1 second, maybe more than 1 second. Okay, now notice that it goes to that cross section basically. And if you want to see the mesh, see the update here, see the update, you click on it, and there is your mesh. So this other slide that I had there, it says if you want to see the mesh, these are the things that I filled in. These, if you want to see the mesh, just update it and you're going to see it. Let's go back. All right, that's pretty much it. So now we're going to go to, ordinarily, I go to the structural scenario creation, but for these problems, I go to mechanical scenario creation. Not this, that. Mechanical scenario creation. And the reason I do this is there are several licenses that I have in mechanical scenario creation that I don't have in structural model creation. For example, ABAQUS, not ABAQUS, but the version of ABAQUS explicit in the 3D experience, for example, the only way I can access it is by going to what I just showed you. Now, first of all, you go here under, you have several options. I go structure, and for the finite element mesh, I create the one that I selected or created. Select the one that I created, and you say OK. Good. So we go to procedures. You don't want to do static. Notice that here is the ABAQUS explicit version of the 3D experience that I don't have it unless I come to this license. Okay. If I go to structural model creation, I don't see this. I see the implicit one, but not the explicit one. By the way, notice that they have removed all references to ABAQUS out of these interfaces, but it is the ABAQUS program. So I go to static step, and in conformity with what the gentleman in the ABAQUS CAE link is doing, is I'm going to use the initial time increment of 0.01. It's a very simple problem, so I just leave it the way it is. This is dummy time, of course. Now, when it comes to boundary conditions, first of all, uh, oh, let me actually, there's some step that I forgot, and I have to go and rectify my oversight. Let's go back to model. Remember where I actually did the meshing and everything? Okay, okay, good. So that's fine. That's fine. Over here, there is abstraction. There's an abstraction right there. There's an abstraction, and you click on it, and over here you have rigid body. See that? Rigid body. I could have done this thing before I actually went to mechanical scenario creation, but it doesn't matter. I went back. Rigid body. Okay. It says the support is we can, for example, select it by mesh part, and it's going to be this part. Okay, the top part. See that? That's one way of doing it. And then, so this is going to be declared rigid, okay? Although I put a material on it, I understand, but it says, where is the reference point? I think in that video tutorial on ABAQUS CAE, the guy is using the reference point up here, but I'm gonna say, okay, you put it at the center of mass of it. So there are some differences, as you can see, the way I'm doing it and the way he has done it, okay? And then that's it. So it's going to create a reference point and put it, actually you can see it's right there, okay? You say, okay. Now we go to where I was, scenario. Remember how to backtrack? Okay, good. So we go to this bottom is completely clamped. So we go to boundary condition, and we use actually, yeah, it's clamped, completely clamped. So this bottom is completely clamped. That edge is completely clamped. Now this point, this reference point, which is the center of mass right now, is going to be moved down by the amount 0.01. So first thing I'm going to say is it doesn't move in any direction but the direction Z. That's the first thing. So let's go ahead here and under fixed displacement. And there are different ways of doing this again. You can say, okay, by mesh feature, and this rigid body right there, rigid body set by mesh feature that by sorry, not mesh feature, FEM feature, and I select the rigid body. So notice that whatever I put fixed displacement is going to put it on the center of mass. It can move in direction Z, but direction R and direction theta is the meridional direction, they're fixed. Okay, but I can make it move down, so I'm going to apply a translation, and once again I can put it, for example, on the FEM feature. It's that rigid body, and I'm going to give it downward displacement of in the direction Z, okay, of -1 millimeter. Okay, good. Now, there is no interaction right now defined between these two objects. If I run it now, this guy, it will run, but this guy will just go through the workpiece. So what I need to do is to go to interaction. First, I define the nature of the interaction. So I say contact property, nature of your contact. Tangential behavior, specify tangential behavior. In that video on ABAQUS CAE, the gentleman puts friction coefficient of 0.5. I use the same value. And for normal behavior, it's hard contact. Hard contact. I believe hard contact is the default, but I checked it anyways. Good. And that's, yeah, and the general contact. So this is defining the contact property, and I click on it. Notice that a contact property has been created for me. If we go down here to the tree, if you go to the tree, you see that in the step, static step, or actually right here, you can see that. Under interaction, a contact property was created. So now I'm going to select that. It's going to select that. and leave everything else as automatic and default. So it's going to find out what the surfaces are, what surfaces, basically make sure that all surfaces are taken into account. See that? Include all edges. So we say OK. All right, before I go ahead and actually run this thing, let me rename this thing to be in case we want to ever get it. So it's going to be Axisymmetric. It was continuum element, and that's it. Okay, hopefully I have not forgotten anything, and we are going to run it. So we go to simulate. First of all, do a quick model check. ABAQUS users call it model check or data check. We went through a simulation check. This is to make sure that nothing serious is missing, and if so, they're going to let you know so that we can fix it before running. Okay, so we say fine, do it. Simulation check. This axisymmetric implementation, which happened in 2021 in the 3D experience, is something very valuable. And I believe that my understanding is that they will be also incorporating plane stress and plane strain version in the future releases. Okay, so that went through, and then we're going to finally simulate. Simulate is the actual running. So you click on it. Yeah. By the way, I forgot to mention that the thing that I'm showing you is for release 2022 of 3D Experience. So it's a rapidly growing or changing or evolving software. They're trying to incorporate all aspects of the uh, ABAQUS program in it. That's why there are rather extensive changes from release, not changes, but improvement from release to release. If you click on the iteration, it's the equivalent of the monitor in the ABAQUS CAE interface. As I said, this is a simple problem. It's going to go through without any issues. In future videos on this problem, I'm going to use analytical rigid surface and for the indenter, and also the one with axisymmetric shells for the indenter modeling instead of continuum elements. So it is going through. Notice that there were some unsuccessful convergence issues here, but it took care of it by reducing the increment probably. When this thing reaches 1, if it finishes, it will hit 1, reach 1, it's all done. Okay. We're not going to be interested in comparing this thing with that video tutorial on ABAQUS CAE. It's just that the process is explained to you. The two obviously are not the same models. The other one is the indenter is modeled differently. It's getting there. We're down to 0.5, 0.6. See, the step sizes are getting bigger. Initially, it will cut down on the increment, but as you go further along, things are going to go faster or going faster. Almost done. I didn't ask for any specific data. It's just a default data that's going to come out. It finished. It's extracting the results, and we're going to look at it in just a second. Let's look at the deformation. Let me close this thing. This is initial increment, which was obviously everything is 0. So if you move this thing on this side, if you scroll down, you'll see that the indenter is actually coming down and interacting with the workpiece, and at the final stage where it goes down to by minus 1 millimeter or negative 1 millimeter, it looks like that. This is the von Mises stress. The numbers are actually in the same ballpark as the other video. If you look at the displacement, obviously this rigid ball is coming down at 1 millimeter. You can see that red is 1 millimeter. Contact now. This can be displayed in 3D also. So if you go here under the display tab, there is this guy results option, and down here there is a sweep axisymmetric option, which it'll sweep it for you 90 degrees. So this slide that I have here at the very end is actually what I'm just showing you now. So we say close. So if you rotate this thing, you see that actually it's swept it by by 90 degrees. You can go 360 if you wish. Something else that I want to show you. If you look at the contact pressure, see, it's kind of hard to see the contact pressure. So one way to see that is to go to display, go to results. There are other ways of doing it too. Double click on the display group. This dialog box opens up, and you, for example, say, show me this part. Okay, so replace this part. See that? The contact pressure is shown here. If you go with this icon, it just flips it, shows it to you with the other one, with the indenter. It hides the other guy. And if you want to see everything, just click on that guy and it shows you everything again. Let me close this. What else do we have here to look at? For example, you can make a plastic strain. This is the here. This is the plastic strain. Obviously, this ball is rigid. There is no plastic strain in it. You can look at, for example, the factor of safety, places where it has failed and it's not, and actually the ratio to the applicable yield strength, and shows you and finally the active region of actively yielding obviously shows you all these points have yielded, but the one out here is still elastic. Okay, I hope you found this thing useful. Wait for the other tutorial when this is done as an analytic rigid surface, and hopefully one where this is at least discussed with doing it as not continuum element, but shell element. Okay.